Welcome everyone, my name is Tatiana and this is my video series on OTF Studio thin film software. OTF Studio is a very powerful, smart and extremely fast tool for multi-layer design, thin film characterization, reverse engineering and monitoring of optical coatings. In this video, I'd like to talk about designing one of the most challenging optical multilayers, dispersive mirrors. Nowadays, we cannot imagine laser setups and ultrafast optics without dispersive mirrors. The multilayers controlling high reflectivity and group delay or group delay dispersion. This is a schematic representation of dispersive mirrors functionality. A short pulse, this is its intensity and electric field in time domain. A short pulse propagates through dispersive medium or dispersive media and accumulates group delay. As it travels, the pulse broadens and its temporal shape can change. So the pulse is getting broader and its shape is changing. If we introduce a dispersive mirror or dispersive mirrors in the laser setup with inverse group delay, the pulse can be compressed to its original size and its original duration. Typical target specifications of dispersive mirrors are high reflectance in a broad spectral range, typically, and reflectance must be close to 100%. And specify group delay dispersion in the same range. Group delay dispersion is the second derivative of the phase on angular frequency. Another possibility is to specify high reflectance in broadband range and a specified group delay. For group delay, it's important to know the form, the target form, and not the absolute position. As I said, dispersive mirror design challenges are typically broadband, and the bandwidth of interest is expressed typically in optical octaves. Today, I will solve a design task. Spectral range is 600-900. That corresponds to the bandwidth of 0.6 octave, optical octave. And the group delay will be minus 40 femtosecond square. I open my OTF Studio project prepared for dispersive mirror designing and apply a template convenient for me according to my preferences. And how to deal with templates I recorded in my previous video. See the link on the top. Here I have everything prepared for dispersive mirror designing: evaluation reflectance plot, evaluation group delay dispersion plot, evaluation group delay, thickness profile is prepared but empty. Then history panel and databases, target database, design database, and layer materials database. All necessary elements are already loaded to the environment panel. We can see here group delay dispersion target, minus 40 femtosecond, high reflectance, 100% target values. And I will use, of course, dispersive layer materials, niobium pentoxide and silicon dioxide. I loaded everything, layer materials, targets, and substrate, and would like to select an appropriate starting design. The first idea is to use a quad wave mirror at the central wavelength of 750, the central of the spectral range of interest. But we can see that high reflectance, this is really high reflectance, but this spectral range is too narrow for this broadband dispersive mirror. Instead of the quarter wave mirror, I will take a good starting design, a chirp mirror. This is a modulated quarter wave mirror with thicknesses from 1.2 to 0.8 quarter waves at the central wavelength 750. How to generate such mirrors, please have a look at my previous videos. The link is on the top. And we can see that this starting design provides already high reflectance in the entire spectral range of interest. But of course, group delay dispersion must be optimized. I switch to design builder panel and start needle optimization with standard settings. It operates very fast, and very fast I obtain a solution, 54 layers in the history, no thin layers, no thick layers, high reflectance in the entire spectral range of interest, starting from 99.6, and the group delay dispersion is oscillating or fluctuating around the target value of minus 40 femtosecond square. Ripples in group delay dispersion are inevitable because they arise from interference inside the multilayer design. These GDD ripples can distort ultrashort pulses, leading to the formation of satellite pulses and transferring part of the pulse energy into those satellites. In GDD ripples, not only the amplitude matters, but also their uniformity, the consistency of the deviation from the average group delay dispersion. For pulse quality, the amplitude is often less critical than the irregularity of these ripples. Let's now verify how these oscillations in group delay dispersion affect the pulses. So what happens with the pulse after interaction with this dispersive mirror, with this dispersive design? I open pulse panel from the analysis ribbon, and here we can see spectral intensity distribution of the pulse. This is a model pulse. And group delay dispersion of the pulse. This is plus 40 femtosecond square. And our target is group delay dispersion minus 40 femtosecond square, because this is group delay dispersion of the pulse with opposite sign. Switch to output intensity distribution. We can see here two pulses in time domain. This blue one is initial pulse, and the orange one is the pulse after interaction with the dispersive design, with dispersive mirror. This is the intensity is almost 100%, but the losses are about 0.9%. So losses in intensity. And these losses, the reason is maybe a little bit higher oscillations in group delay dispersion, but nevertheless, although the oscillations are quite big, plus minus 40 femtosecond square, we have only 0.9 losses. This is very small value. I will save this design. I saved this design and will try other solutions, other approaches for this design challenge. Now I would like to try another approach. I would like to suppress group delay dispersion oscillations using range targets. I load a range target that limits group delay dispersion deviations from its average value by plus minus 20 femtosecond square. I take the same starting design and I apply the same needle optimization method. And very fast we obtain 54 layer design again. No thin layers, no thick layers, but GDD oscillations are suppressed. So there the amplitude is now 20 femtosecond square. What I don't like is this feature in group delay dispersion, this irregularity. And this irregularity can lead to pulse, problems with pulse, to energy loss. We should take in mind that reflectance and group delay dispersion are interconnected according to physical reasons. They cannot be optimized independently. If we suppress group delay dispersion very strongly, we can worsen our reflectance performance and again obtain energy loss. Let's verify this design using the same feature, pulse analysis. I return to my previous target, open pulse analysis panel, and analyze output intensity. We can see here this orange pulse, it's almost 100% intensity, but nevertheless there is some loss of energy, about 0.9%, the same as in the previous design process. So oscillations are suppressed, but nevertheless we have small loss. And now I will show another design tool, another design approach that will help you to solve such challenging design problems with dispersive mirrors. To demonstrate another design approach, I load my good starting design, again, chirp mirror, but instead of group delay dispersion target, I will load group delay target. OTF Studio has a tool that allows you to recalculate group delay target to group delay dispersion target, and in the opposite direction, group delay dispersion target to the group delay target. Dispersive mirrors are defined by relative group delay, not absolute group delay. The target group delay is not uniquely defined. Only its shape matters, not its absolute values. This means that a constant group delay shift does not change pulse compression. If we shift the target group delay by an arbitrary constant, it will mean a time axis shift of the pulse and does not affect the pulse shape. It's possible to relax target requirements by introducing a so-called floating constant. OTF Studio provides the floating constants tool that enables you not to require that the group delay to be fixed in absolute values, but relax target requirements. I apply the same algorithm as before, needle optimization standard, and very fast obtain a good design. 54 layers. This is its structure. No thin layers, no thick layers. Excellent correspondence to group delay target. You can see it from the plot. High reflectance, higher than 99.9% in the entire bandwidth and the entire spectral range. And let's load now group delay dispersion target. You can see ripples in group delay dispersion, but these ripples are symmetrical and regular with respect to the average level of group delay dispersion, of target level of minus 40 femtosecond square. Let's check it on the pulse. Open pulse analysis panel. This is the same model pulse as before. We switch to output intensity panel and zoom the plot. So this blue is input pulse and orange is output pulse. We can zoom and zoom and zoom this pulse, and we can see finally that the loss, energy loss, intensity loss is negligible for this design. So output intensity is almost 100%, although we have ripples in group delay dispersion. And the level of these ripples is about 20 femtosecond square. But due to regularity, it doesn't affect the pulse compression. This is a nice method for dispersive mirror designing. Typically, the dispersive mirror design challenges are defined by two factors: bandwidth and the required group delay dispersion level or group delay pattern. For successful designing, the key elements are target specifications, target tolerances, suitable design algorithms and their combinations, and starting designs. In the next videos, I will show more design examples and OTF Studio tools for designing dispersive optics. Thank you for watching. If you have questions, feel free to reach me, and see you in the next video. Bye!